Hello, Algebra 1 students. This is Mr. Round. I'm putting together a little review video to demonstrate topics or ideas, skills that we should have picked up going through sections 10.1 through 10.4 in the Chapter 10 note packet and through textbook practice. And I may be representing your teacher as well, so we're kind of sharing some of the load here and putting out videos and things like that. So we are preparing you for a little Google form check quiz that should be coming your way. But what I'd like to do on this is I'm going to just demonstrate how I do these problems. It may be a little different from the way maybe your teacher showed you, but just think of it as kind of learning how to do this in maybe another way that might also help. I'm going to do each problem. If you know how to do it, I would just go for it, try the problem, and then maybe check with my solution, see if it matches up. If you have no idea on how to start it, you don't remember, you could watch me do it and then go back, rewrite the problem down, try it, and then match up your solution. You have tons of extra practice on the homework problems you've done that you could check. You could also go back to your note packets. This will be an open notes little Google form quiz anyways. You can go back to your note packets, look through, and try problems that we did in the video lessons and then check your answers on that. So you can go ahead and practice. We'd like you to try and do this Google form quiz on your own without, it'd be awesome if you could do it without even looking up in your notes, but it is open notes and calculators are allowed. So I'm going to even bring up the calculator and show you some tactics I would try with the calculator. So these are just the big ideas, what we think are some of the most basic problems. So here we go. I'm going to go through these with you. So the first one is goes with simplifying radicals. We've got square root of 540. This is a super important idea as you prepare for geometry and your trigonometry course. You'll be asked to write things in exact form and simplified radical form as you move into some right triangle trigonometry in the future of your math. And so it's an important topic here to know how to do and have a method to approach this. Now we approach this with using a factor tree, looking for all the factors of this number, all the prime factors, and then looking for pairs. And each time you see a pair, we know that that represents a perfect square. And one of the pair of those numbers comes outside of the radical and is multiplied by any of the others. And I'll demonstrate what that looks like here. So we're going to get started with this 540. You might look at this and think, man, that's a big number. I don't even know how to start. You know, it's even, if it's an even number, you can always divide it by 2. I mean, you can go and start with your calculator and just do 540 divided by 2, and that kind of brings it down a little bit. And say, oh, at least 2 goes into it, and now we're down with a value that's half of that. And you could divide that by 2 maybe again. So you can always start that way. It looks like we could divide it by 2 a couple of times. Some of you might see that 54 is just a product of 9 and 6, and so you might do, 90 times 6 or 9 times 60. You might approach it that way in the beginning. But let's just go with, say it's a big number. We don't see that 90 and 6 go into it. We just start breaking this down a little bit by taking out a 2. So I have 2, and it was 270, and the 270 is 2 and 135. And we don't want to lose any of these values. This is called a factor tree. These are like roots right here. And down at the bottom of this root right here, it's kind of terminated or ended here. We've got a 2. And then as we go down here on the 270, we have a 2 and a 135. So another 2 is the bottom of our root. We don't want to lose any factors. Keep track of them here. The 135, I know 5 goes into it. So go to your calculator, figure out how many times 5 goes into it. We know 5 goes into it. Goes into 13 twice with 3 left over, and then goes into 35 7 times. So we have 27 here now. And then 27, you might quickly think of 9 and 3. Move this down a bit. And then 9 would be 3 and 3. And so what we have going on here, if you just kind of look at your bottom, just kind of travel along here, and then down around here, and over here, you have this bottom of the root system with a bunch of prime factors. As a matter of fact, there's a theorem, or it's called the fundamental theorem of arithmetic, that says any positive whole number can be factored into a product of primes to different powers. And so that's what we're seeing here is all this bottom, you see 3s, 5s, and 2s, and they're all prime numbers. So we don't do this with a factor tree, but what we really mean as we break these up is that each one of these has a radical over the top of it. And so there's a radical over this, a radical over this, a radical over this, and this, and this, and this, all the way down. And so what's happening is that each time we have a pair, say we have a radical 2 and a radical 2, that's equivalent to the square root of 2 squared. And we learned in this unit that the square root of 2 squared, the square root of anything squared, is just the thing underneath the radical. In other words, the squaring undoes, or is the inverse operation of the square root. And so we end up with just a 2 here for that. And so I'm going to go back here and let's just get rid of these little radicals. We don't usually write those, but you need to understand that they are there all the way through. Like it wouldn't be a true statement if we didn't have those all the way through. But we have all these guys with radicals over them all the way through as we go down. And so that's how that works. That's why every time there's a pair, we have a perfect square. And let's go ahead and put this back in. There's our little that and that, that and that. That's the number 27. We have a 9 and a 3, and the 9 becomes 3 and 3. So what we're doing is looking down this bottom layer here and finding all of our pairs. We're going to pull out one of each pair out of the radical, and that will be our simplified version of this. So it will look like this. This is equal to, we've got a pair of 2s there. And so we'll pull out 1, 2 from the radical. We've also got a pair of 3s down here. So we're going to pull out a 3 from the radical. And then what you'll notice is I have a 5 without a partner and another 3 without any other 3 to go with it. Those will remain underneath the radical. And things that are not under the radical will get multiplied together. 2 times 3 is 6. And things underneath the radical, the 5 and 3, will also get multiplied together and give us 15. And that's our simplified radical form of square root of 540. And so 6 root 15, it's an exact answer. It's simplified. There are no other perfect squares to pull out of that 15. And we're done with that. All right, let's go on to the next one. We involve variables. Now with variables, it should be noted that any time you have an even power on a letter, it is a perfect square. Odd powers, you're going to have a perfect square will be 1 less than that power. So this 5 right here tells me that I am going to have an x under the radical in my final solution. And I have an x to the 4th underneath that, that is the highest even number that is contained within that x to the 5th. So it looks like this. Think of it this way. We've got 64, so we would simplify the number in the same way that we just did that 540. It just so happens 64 is a perfect square. That is 8. Now, because I have an odd power on that x, I will have an x to the 1st left in my final answer. But if I were to do, say, a factor tree on this, I have 1, 2, 3, 4 x's here, and then one more hanging out in here. I have 5 x's, but I have 2 pairs of x's. And so that would tell me, aside from the 8 that gets pulled out, I have an x and an x that gets pulled out. Or think of it as these 2 pairs of x's I circled represents x to the 4th, and the square root of x to the 4th would be half of that power, which is x squared. So we're going to end up with an x squared coming out of the radical. The y to the 6th, if you can picture 3 pairs of y's, we're going to end up with y to the 3rd on that one. And like I said, this x and x will become x to the 2nd. And then I still have a square root of x left over. It's this guy right here that does not have a pair. It ends up staying underneath the radical. When you simplify these radical expressions with variables, you will, if you have an odd power, you will have a single power of that variable left under the radical. And if you have even powers, it's a perfect square and you won't have any of that variable left under the radical. Like this y to the 6, you could think of it as 1, 2, 3, 4, 5, 6 y's. We've got 1, 2, 3 pairs that come out. That's y to the 3rd. So 8x to the 2nd, y to the 3rd, times square root of x is our final solution on that. All right, got a little division problem here. This one, square root of 20 over 36 is the same as the square root of 20 over the square root of 36. One thing to watch out for, and we just saw it in the previous one with that 64, is if it's a perfect square, take the square root of it. And you can do that on your calculator. If you don't know if it's a perfect square or not, you can go to your calculator. I could check second, hit the x squared button. Because those are inverses of each other, x squared and square root, the square root button is typically right above the x squared on a lot of calculators, not all of them. But you're going to type in 20, hit enter, you get a decimal value. That means 20 is not a perfect square. You probably already knew that, but let's just check square root of 36. That is a whole number, so square root of 36 is 6. So we can go back. We can rewrite this as square root of 20 over 6. Now square root of 20 can be simplified further. It falls into the category of the very first problem we did up here with that square root of 540. Square root of 20, I'm going to have to do a factor tree on it. You might do 4 and 5, and then the 4 becomes 2 and 2. 2. And so I have a pair of 2's, so the 2 will come out, and then just a single 5 that stays underneath the radical. So I have 2 root 5 over 6. So I've simplified that root 20 to be 2 root 5. Right here, if you just saw 2 over 6, you would know to simplify that. Those are both even numbers. They have a common factor of 2. 2 goes into 2 one time, leaving just 1 root 5 on the top. And it goes into 6 3 times. Typically, we will not write the 1 in front of the radical 5. It's an unwritten 1. So you'll see the final solution is root 5 over 3 in simplified radical form for that. All right. 3 plus root 2 times 3 minus root 2. We call these conjugate pairs in upper level math, but something interesting will happen with this one. This is a good big idea. We did lots of multiplication and distribution. It was good practice. But this particular problem is a really good one because it relates to some topics that you'll see in Algebra 2 and beyond. So something interesting will happen here. Let's go ahead and go through this, just doing the multiplication. You could be using FOIL or the distributive property. 3 times 3 gives me 9. 3 times root 2 with that negative sign in there. Think of it as 3 times negative root 2, or copy the sign over and do 3 times root 2. I cannot multiply the 3 that is not under the radical by the 2 that is. So we're going to just write this as the product 3 root 2. Treating the root 2 just like if it were an x. And then the next one here, root 2 times 3 is positive 3 root 2. And then the final distribution is that root 2 times root 2 that we talked about earlier. And root 2 times root 2 is the same as root 2 squared, which the squaring cancels out the root, or gives us 2. Another way to think about it is root 2 times root 2 is root 4, and the square root of 4 is a whole number 2. And so that's what I end up with as that last term. It's a minus sign because of the positive and negative out in front of those, and then 2. And we'll notice on this that the 2 middle terms on this particular one, this and this, have like radicals attached to them. So we can go ahead and add them, add the numbers in front of the radicals. So negative 3 plus 3 is 0, and the 0 root 2 is gone. That term is not written down, they cancel out. 9 minus 2 gives me 7, and so that expression, 3 plus root 2 times 3 minus root 2, ends up equaling 7 in simplified form. All right, so it's multiplying, a little bit of multiplying, just distributing really. And that's a good one to know how to do. All right, we're going to move on to the next page here. We've got another problem here that has to do with like radicals. And I chose this one because I want to just address, well, for one, they do have the same number underneath the square root symbol, or radical. And there's an unwritten 1 in front of this square root of 6. And so what I am actually adding or subtracting are the numbers in front of the root 6's. So 1 minus 5 gives me negative 4, and then times root 6. And so this falls into the category of like radicals, and so you would add or subtract the numbers out in front of the radicals. Excuse me. So negative 4 root 6 is the final solution on that. You might look at root 6 and think, man, that should be simplified. But if you do a factor tree on root 6, you'll notice we have a 2 and a 3. Neither of those have a pair. So this thing is simplified when it is done. All right. Finally, we wrap up this section. Actually, we're going to go back and do the Pythagorean theorem stuff from the first section in a minute. But this was from section 4 of chapter 10. Solving equations with radicals in them. And the big idea here is that we square each side of the equation to do that. The other thing we really need to be aware of is that we need to check our final solution, because when you square each side of an equation in order to find a solution, you could be finding potential solutions that do not work in the original problem. And we call those extraneous solutions, and we don't want to include those in the solution. So you should just make it a practice on these equations with radicals in it to just check your answer. So the process that we're going to go through on this first one right here is we're going to isolate the square root symbol expression first. So don't jump right into squaring each side. Get that square root by itself first by, in this case, subtracting 4 from each side. So I have square root of 2x equals 6. That's the first step. If there had been a number in front of the square root symbol over here, like say a 3 or something like that, I would have to divide 3 by 3 as well. But we're going to subtract 4 from each side. Next step is go ahead and square each side. So it looks like this. And the squaring undoes the square rooting, leaving us with 2x equals 36. And then I just divide each side by 2. So x equals 18. And we're going to check 18 in the original, just see if it works or not. So up in the original, I've got square root of 2 times 18. I'm putting the 18 in for the x there. Plus 4, does that equal 10? Well, 2 times 18 is square root of 36. Plus 4, does that equal 10? Square root of 36 is 6. And 6 plus 4, I think at this point we can clearly see that it does work. 10 equals 10. And so this is the solution. You can go ahead and box it now. If for some reason we had 1 or 2 solutions and one of them didn't work, we would cross that one out. If nothing works in the original, then we have no real solution to that equation. We're going to just focus on these two here is all I'm looking at. But this one has a solution. You should get in the habit. It'll pay off as you move on in math to go ahead and check your solutions, especially on these equations with radicals in them. All right, this second one here. Everything has a radical over it on each side. There's nothing to add or subtract from each side or divide or multiply. We're just going to jump right into squaring each side. We've got 5x minus 3 equals 2x plus 15. And from this point on, pretty basic equation going back to the beginning of our semester. I like to collect the variables first, so I would subtract 2x on each side. That's what I would do first to get a positive 3x minus 3 over here on the left equals 15. If you added the 3 first, which a lot of students do first, that would be fine. Add 3 to each side here. So we have 3x equals 18. Divide by 3. And x equals 6. So we're going to go right back up to the top here. X equals 6. And we're going to plug in that 6 for x. And so here I have, I'll just write it above, square root of 5 times 6 minus 3. Does that equal square root of 2 times 6 plus 15? Well, if you do the arithmetic here, on each side, you'll notice that 30 minus 3 is 27. So I have a square root of 27 on the left. And 2 times 6 is 12. 12 plus 15 is also 27. So I know I have a square root of 27 on each side of the equation. So they are equal, meaning x equals 6 is a solution to that radical equation. All right, so I saved my favorite for last. I have Pythagorean theorem here. Hopefully you have this memorized. There's really 2 cases that these problems fall into, and I have one of each case here. You'll see it on the Google quiz. We've got the case. Well, first of all, let's write down our formula. We've got a squared plus b squared equals c squared. And that formula works for a right triangle where c is the hypotenuse. And A and B are the legs in any order. So if I have a right triangle here, my one case is when I'm given the legs. So here I'm given a leg of 7 and a leg of 24, and I'm asked to find C. In the second problem here, it's the other case. Draw our generic right triangle here, not necessarily to scale. But we've got here a leg of 7. We've got a hypotenuse of 11, and what we don't know this time is the other leg. So it falls into one of 2 categories. Either you're given the 2 legs and you're asked to find the hypotenuse, or you're given the hypotenuse on one leg and asked to find the other leg. And the algebra for these 2 are just slightly different, but these really represent the 2 different types of problems you might get when it comes to solving for a missing side length in a right triangle using the Pythagorean theorem. So on this first one, I have let's call A7. So 7 squared plus 24 squared equals c squared. You may know 7 squared is 49. 24 squared, we may not know. We go to our calculator, type in 24, hit the x squared button, and I get 576. So 49 plus 576 equals c squared. Then go ahead and add the 576 and 49. So we can do 576 plus 49. That gives us 625. So I've got 625 equals c squared. And then we take the positive square root of each side. So c equals whatever the square root of 625 is. Not sure what that is. We'd go back, hit second in the x squared button, do the square root of 625, and you'll find out that it is 25. As a matter of fact, teacher talked about this called a Pythagorean triple, and we love triples in geometry and trigonometry. 7, 24, and 25 all go together, creating a right triangle. So this is equal to 25. And triples show up all over the place in mathematics as you move on. All right, the second one on here looks a little different. We're going to put the 7 in for A. We don't know B, and we do know C. So we're still going to square each of these numbers. But then when it comes to the algebraic process of solving, instead of adding the 2 numbers up, A squared and B squared, and then taking the square root, we're going to have to subtract the 1 term over to the other side, or from each side. And so I have b squared equals whatever 121 minus 49 is. And that ends up being 72. And we're going to go ahead then and take the square root of each side. So b, just the positive square root here, because we're talking about the length here. So square root of 72. And then depending on the what the question is, if this were a real life problem, where you're, going to go and buy a board of length square root of 72, at that point you might plug it into your calculator. You might hit second square root 72 and get a decimal approximation. It ends up being about 8.5. Maybe that's in feet. So you get about 8.5. And we use little squiggly equals here. B is squiggly equals 8.5. If you're just doing these problems, and they do ask us to do this often in geometry, trigonometry, is, what's the simplified radical form of this? Well, this goes full circle to that first problem we did with the square root of 540. You take that square root of 72 and you do a factor tree with it and find all those pairs. Just give you it right here. And so, 72, you might do, I know that's 2 and 36, and 36 might be 9 and 4, and 9 is 3 and 3, 2 and 2, something like that. We've got a pair of 3s, a pair of 2s, so this ends up equaling 3 times 2, and then 1, 2 left over, so that stays under the radical, so I end up with 6 root 2. And so here it is in simplified radical form. 6 root 2 is the value of b, and then as a decimal we see it over here, b equals about 8.5. And so when you were doing these problems, we hadn't yet learned how to simplify. If you remember, Pythagorean theorem came before the section on simplifying radicals, and so we were not doing it this way. And so you'll be asked to do it just in decimal form on these Pythagorean theorem problems, but I wanted to show you that it does apply. Simplifying radicals, this is how we use it in geometries. We might write the solution in exact simplified radical form as 6 root 2 instead of the 8.5. Although, if you go to Home Depot and you ask for a board of length 6 root 2 feet, they might look at you funny. But it'd be fun anyways. So, but 8.5 feet, we could do that. So it kind of depends on the scenario. Real life sorts of deals, you're going to find a decimal approximation. When we're doing upper level math and we want exact answers, we're going to leave it in simplified radical form. So hope this helps. Good luck on your Google form quiz. Thanks for listening.